Hello, everyone. First of all, big thanks to the Pygrunn organizers and allowing me to present something that I'm very excited about. So the plan for this talk is simple. I would like to use this 20-25 minutes that I have to make all of you here sort of big data experts. Maybe not experts, but to enable you to work with sort of big data. So can we have a quick show of hands? How many of you would say have worked with big data or can give me a big data definition? Okay, so this 1 billion samples, it's not big data by my definition, but it's sort of largish data that many people, many data scientists, especially the less experienced ones, are not so comfortable dealing with, especially if you don't have the privilege to work with big clusters or have a nice company that can fund your AWS or Google Cloud habits and so on. So a little bit about me. I'm this guy. I was an astronomer here in Groningen. Now I'm a data scientist for Xivia Labs, where I do DevOps and I do models for release orchestration and automation and continuous delivery. And I'm also co-founder of this Vex.io thing that I'm going to present today. It's all open source, by the way, so it's free to use for commercial research and hobby projects and so on. This is my friend and collaborator, Martin. He's the main author of Vex, the library I'm going to present today. He has the largest media presence of our team. And these two guys just help us develop the product and give us more experience from having worked with clients of different branches, different products, different solutions. So where did the idea started? Me and Martin were both astronomers here in Kaptein. We're very privileged to work with this satellite that is a hot thing now in astronomy. And we had a problem. We had a data set with 1 billion observations. It actually turned out to be 1.5 billion. But our boss didn't really want to give us money to spin up AWS clusters and do analysis there. So we didn't know what to do. First, from a technical standpoint, and from a second standpoint, well, you have a lot of data. You've never seen it before. What do you want to do it? Rule number 1 in science, you plot it. If you want to plot 1 billion points, and you will use a scatter plot, yeah. So then we thought, okay, you have a lot of data. If you just want to use individual stars, in our case, maybe that's nice for some cases, but if you have big data, you really want to use aggregation. So what we focused on is creating density maps. So then now, if you create a density map, you don't just see a full blackness, you see some structures, and this is an early data release, so there are lots of problems, but basically you see something. And this is where Vex started. It was made for astronomy, but then we met this guy on the right, Jonathan, a more experienced data scientist who saw the potential and said, oh, look, if you repurpose this and make a pandas API and just cater to a little bit to different fields, you can have something really fun that you can help people here. And that's what we did. So instead of just having slides, I decided to do something very brave and give you a very honest demo of what Vex is. So Vex employs some concepts that allows you to work with, I would be brave enough to say, as much data as you can fit on your hard drive of your local machine. And so I will assume that everybody here knows about the Jupyter Notebook. Is that okay? Everybody has used pandas, more or less, and everybody has at least heard of scikit-learn. Great. So let's get started. Well, import stuff. Vex, some color maps, and stuff for plotting. And now, different notebook. I will import things again. So Vex employs this concept: memory mapping, expression system, and lazy evaluations. Of course, we have efficient algorithms, and we focus on data aggregation. So I'm going to use this taxi data set. It has the taxi locations, pickup locations, daytime, anything you would like to know if you were a CEO of a taxi company between 2009 2015. And on disk, this single data file is 107 gigabytes. I have a nice fancy machine here, but I do not have 100 gigabyte RAM, and this is a kind of off-the-shelf MacBook that I got from my current company. So if the file is memory mapped, it opens instantaneously. What memory mapping does is not actually reading the file, but the operating system tells Python, look, the file is here, this is the structure, it has columns, it has rows, and if you want to start reading it, you can read it from here. There is not actual reading doing, but you just tell Python, oh, the file is here on memory, on the disk, do whatever you want next. So then, if we just want to make a preview, kind of like pandas, even though we have 1 billion rows, or actually a little bit more, we read it instantaneously, because we're not reading the whole thing. In this case, we have a preview of the first 5 and the last 5 rows. And we can explore the contents just like we do in pandas without having to read anything into memory. We can do info, gives you a little bit more about the data set that you have, some metadata. If you're a scientist, maybe you want to explore the columns, add units, descriptions, and so on. And of course, you have a preview of your data just as before. So the whole point of X is not to use columns in memory, but to use expressions. And we wanted to make this data science friendly, cross industries and cross academia, industry, domains. So we wanted to be as close to pandas as possible. So if you want to view, let's say, the trip distance of this taxi data set, you can just view it as if you do it in pandas. You get some nice information. And you see, even though I have 1 billion rows, I view it instantaneously. We have support for datetime. And of course, we have these expressions that if you use any mathematical expression that you want, and by expression I really mean x plus y plus z, and anything that you would write on paper, you get the result instantaneously, just because you're not calculating everything, you're just calculating the first and the last 5 rows to give you a simple preview. That's the concept of X. So let's say we have another expression. If you want to say the total amount a passenger paid versus the trip distance, it's calculated instantaneously. And you can add this as a virtual column in your data frame. It's not really a column, it's virtual, because all Vex memorizes, it's your mathematical expression. Divide A by B. And then if you want to look it up, it's appended at the end, but it's only being evaluated when you need it. So now we come to the concept of things being lazy. So Vex is lazy. It means that things will only get done if they must be done. Okay, so here, I want to calculate the mean trip distance. Now I'm actually using the full billion rows, and this is the mean trip distance in miles. Let's say I want to use this, the fee over distance, how much people paid divided by the distance. And there are already problems. Oops, a none. So if it's a none, usually you divide by 0. So maybe we want to filter things out. The API is exactly the same as in pandas. We filter things out. And this is the result. So maybe this is not impressive, but I'm using 1 billion rows in real time to do some simple statistics. A feature that I really like about Vex is this called name selections. You can do the data frame.select, write your expression or any Boolean expression that you want, and give it a name. You can have multiple of this, and then use almost any method in Vex supports this selection keyword. You can pass off the selection, and all the maths will be done with a single pass over the data for the multiple selections. So you don't have to do things again and again and again. It optimally uses the resources. So Vex is made really for data aggregation, so this is where it shines. We can do statistics, 0-dimensional, kind of like counts. It's really fast. We can do 1-dimensional statistics. So this is, if you want to count something, when you bin by a certain value, let's say you would bin by latitude, then you can easily plot this. And we can do this in 2 dimensions. So bin by 2 quantities, given a shape and given certain limits. And we can easily plot this. The plotting is done simply by matplotlib. So we also include very nice wrappers around matplotlib. So if you simply want to do histograms, you get nice axis labels, the column names, and so on. You can do this in 2 dimensions. So see, no need for a single computer. This is the entire 1 billion rows plotted. This is the pickup locations, and you see a nice map of Manhattan and where people basically get taxis from. How fast is it? Okay, let's do, this is a simple thing around, wow, it goes faster than I can talk. This is for my selections, 2 selections, 2 maps, 3 seconds, 1 billion points. This plot function, it's a wrapper around matplotlib, but it's quite fancy. You can use nice keywords like this, where you can say, okay, I want to have a 3rd column, like a z direction, bin by this, and then what do you want to do with this? Well, let's say I want to know the count, and I want to know the mean of certain quantities. And then you can say, okay, How do I display this? Well, the columns will be the binning, and the rows will be the what, or what I want to say. And for data exploration, you get nice, simple. It's more or less a gimmick, but sometimes it's useful. Okay, then what happens if you have heavy calculations? So VEX uses this expression system, so everything that you specify is not calculated in memory, but only calculated when needed. So let's say I want to calculate an arc distance, and this is a complicated expression. It has arithmetics, trigonometry, square roots, and so on. So it's quite computationally expensive. Let's test it out. This is the kind of different distance between Groningen and Utrecht, where I live now and where I used to live. More or less correct. I can do this for the entire data set and see if it's getting calculated for a few seconds. And I see it at the end. Okay, so now let's do the whole thing. Let's do a sum of this. So now this complicated expression is being evaluated in real time, and we're taking the sum. So it doesn't exist. It only exists as a mathematical formula. And this is a complicated expression, so we wait maybe half a minute to do, maybe more because it's a live demo. When I'm alone in my room, it goes really fast. And there, took 23 seconds. So in VEX, as long as your expressions are using NumPy functions or just pure Python, we can do JIT. This stands for just-in-time compiling. So if we now have the same expression, but use this JIT_numba method, we use numba to compile this in C in real time and use the underlying C libraries to do the computation instead of Python. And this should be a little bit faster. And there, done in 11 seconds, roughly half the time. The number is a bit different. It's because I'm using float 32. If I use float 64, this data set would not fit on my hard drive, and this NumPy is not really made to use for float 32, so I'm getting a little bit of rounding error, and it's not a little bit, but it's a little bit, but when you have 1 billion things accumulate. Okay, so that's more or less VEX. So now let's do some serious data science. Let's do a real, if you have this data set, and imagine you're director of a company, taxi company, you want to have some insights. Let's do the standard things you would like to do. But let's say your data scraper gave you this data for the first time. You're kind of used to using pandas, so you say, okay, I'm going to try this new thing, but I know how to use pandas. First, you're going to view the data set. It looks like this. We already did that. Then we have this describe button. This describe, I think it exists in pandas. You can correct me if I'm wrong. I think we stole the idea from there. Basically, what it does, it's computing the counts, the number of missing values, the mean, standard deviation, mean and max of all the columns that are in the data frame. So now I have this many rows, 1.1 billion, and I have 11 columns, and I will try to do this in real time. So because I know it's going to take about a minute or so, I'm going to open this activity monitor, because maybe you're wondering, okay, does this guy really using 1 billion columns or something? So I'm going to use this activity monitor to show you how much RAM I'm actually using for doing all of this. You may think it's this one, but this is the previous notebook. Actually, this is the process. So actually, VEX is fully parallelized. All the computations are done as much as in parallel as we could make them. And the memory is, wow. Can you read this? This is the memory I'm currently using to do this 1.1 billion data set on my laptop at the moment. I think this is the slowest part of the talk. After that, it's going to be quite fast. Actually, maybe I can ask for a favor. Can somebody take a photo of me when I'm giving the talk? I want to show it to my mom. I dressed up for her, not so much for you, but for her. She'll be proud and stuff. Maybe I'm explaining something? No? Come on. And there it is. So 19 columns, 18 columns, 1.1 billion rows, and we get all the statistics. So let's do some data science. First, we want to remove some missing values. This is the missing value column, and we see that, wow, this column that I don't even understand has a lot of them. Let's ignore it. This rate code has a lot of them. Let's ignore it for now. Drop-off locations, those are probably important. So I'm going to just drop them. And there was pickup latitude, there is 1, so I'll include that one as well. So I'm going to drop this. And it's instantaneous. And it's instantaneous because I'm not really dropping it. I'm just telling Vex, when the time comes to do actual serious computation, drop it then. Now I'm just remembering the command or the expression of what I want to do. Next, let's say I go and look at the number of passengers and say, oh, max number of passengers, 200. That's got to be a mistake. So let's see the unique number of passengers. Wow, range of numbers. So my taxi company doesn't have buses or something, and even buses cannot fit this many. So let's say I'm going to take more than 0, because there is also 0 passengers somewhere. Here it is. And less than 10. Maybe they're babies, or maybe I have minivans or something. And done. That's the selection. OK, now let's see the distribution of distances. So if you are a data scientist and you use pandas, this value counts method is your favorite method to use. I see one person noting. It's also my favorite method here because we're using extreme kind of number of rows. We've included a progress bar to see kind of how much you're going to wait. And this is the distribution, 1 billion, like 10 seconds, not that bad. But we see a lot of things, a lot of distances that are 0. So I'm like, oh, OK, maybe we want to drop them. Let's actually plot the distribution. This is what it looks like. Wow, there is a big tail. Let's see what is the max of the trip distance. Wow, 10 to the 8 miles. That's like 100 times the distance to the moon, so we don't want to do that. Let's make like a small zoom in and go, oh, OK, from 0 to about 10, 20, it's a reasonable thing. So let's take within 10. This is miles. OK, so I call this bit, what is New York City? If there are this many outliers in the passengers and in the distances, there got to be some outliers in the distribution of pickup distances. And as a manager, I like to know where people take their taxis. So in Vex, we have this plot widget that you can interactively plot your data. Wow, there is nothing to see, but I see a smudge. So let me zoom in. Whoops, I cannot zoom without a quick wheel. So this is actually creating a histogram in real time of the data. With using 1 billion points and all these filters and stuff like this. Let's zoom, 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 zoom. I should have brought the mouse. OK, there it is. And I can zoom in even more. And this is dynamically updated. And we can also do interactive selections and stuff. And this is great if you're a scientist or if you need to analyze a data set that you've never seen before. Even though it's 1 billion rows, we can do it interactively. So OK, I decided this is going to be my New York. Everything outside is a mistake. I'm going to define some boundaries. I'm going to make a selection just as in pandas. And I'm done. OK, now let's define some new features. So let's say I want to look at the speed. This is distance divided by time. Then I want to define the duration. This is just time in minutes. And I want to look at this fare by distance. So maybe how far I'm going is not enough, but I want to see what is the optimal kind of metric. And this would be how much money I get divided by how far I go. And you see this is really fast because nothing really happens. I'm just remembering the mathematics. OK, let's see how the time distribution looks like. So now I would like to kind of describe this line, because it's going to take a while. So this is a virtual column. It's being calculated as we're waiting. I also want to take the log. This is just a short-form function. And this limits, usually, if you have a range or something in matplotlib, you define a number, like from 0 to 10, or some number. Here you can also define a percentage, which means now I'm taking 95% of the data. So the 5% that are outliers, I'm going to discard them automatically. And this kind of guards me from just seeing one big spike, where like a big one distance that went to the moon, and so I don't care about it. So here I'm actually doing two things. That's why it's a bit slow. First, I need to determine the data, and then I need to plot the data that I've determined. And I need to take into account all the selections and filterings that were done before. More pictures? No? OK. I'm going to execute this right away. so I don't have to wait so much. And there it is. So there is still a lot of time, like maybe the meters were wrong or something. So I decided, okay, the trip durations I'm going to take within 5 hours. If someone is crazy to stay 5 hours in a taxi, and 0. And then let me look at some datetime data. So from this, from the pickup hour, I can extract the hour, just like in pandas. I can extract the day of week and the month. Here, the month I subtract 1 from the month because I want everything to start from 0 because the hour starts from 0 and the day of week starts from 0. So it goes from 0 to 6. So Sunday is 6, not 7. I think it's the same in pandas. Here I have a nice way because all these values that I'm getting, hour, day of week, and month, are basically, I can treat them as categories. So I'm just saying, okay, all these values, don't treat them as numbers, but treat them as ordinal categories. This is what this does, and then I can simply plot using the same function as before, and Vex knows that even though these are numbers, treat them as categories and just plot the counts. And let's get some insights. So the redder the color, the more taxi traffic there is. So you can see after midnight or midnight, Friday, Saturday nights, popular nights. Here after work in the weekdays, popular. In the middle of the night, during week hours, not so much. So I'm able to do this in 13 seconds. 13 seconds, this is for a month. Let's say day of week and month. For some reason, Saturday in March is great, and also Saturday in October is great. Maybe there is some event in New York at the time that I don't know about. Another favorite thing, group by. So I'm going to do a group by. API is exactly the same as in pandas. I'm going to group by hour, and I'm going to calculate the mean of the fare amount, the tip amount, this fare divided by distance metric, the trip duration, and the trip speed. And out of this, 1, 2, 3 are virtual columns, so they're calculated on the fly for the full data set that I have. I have another thing here. Let me execute that as well. As I said, this is going to be an honest demo. So there is no pre-computing and there is no cheating. OK, so this is how it looks like. We see, OK, the tip amount, people around midnight and in the morning tip the most. The speed is highest, 5 o'clock in the morning. Probably there is no traffic. And this is kind of inverse of the trip duration. And this is still being calculated. And this fare by distance, I guess it's most valuable for the taxi driver to work around the rush hour times, of course. And this took half a minute to compute. All the statistics grew by 4 billion columns on my off-the-shelf laptop. And I'm using 3 gigabytes of RAM to do this at the moment. OK, this is for months. I don't want to spend too much time on this. It looks like this. It's possible. Density maps, we already saw that we can do this. And just to show a nice performance, this is a simple density map of the filters that we did of New York City. And just to show what the performance would be, I'm doing 2 plots at the same time where I have a filter selection. Let's say I want to see where people get their taxis from in the morning before they go to work, so between 6 and 9 on the weekdays, and the same where they get the taxi from when they, well, sorry, not where they get the taxi from, but where they're going. I want to know where they're going in the morning and where they go in the evening. So I've already demonstrated that I can do this, but I just want to show you what would be the kind of real-life performance in real time. I'm doing 2 plots simultaneously, and also all of these selections, like these 3 quantities or 2 quantities, are virtual, so they don't exist on disk. Okay, can I ask the organizers if I can have 1 extra minute to show my favorite part on top of this? I'm not going to do an explanation. I'm just going to run the notebook. It's not going to be slow. Sorry?
Let's end with the bombshell.
Yes, this is the bombshell that's coming after this. And there it is. 1 minute, 10 seconds, 2 plots for billion points, no Hadoop, no clusters, no Spark, no nothing. I mean, you can use it if you want, but by the time you set up the cluster, I have this. The bombshell. Now I'm going to do machine learning very quickly. I'm not going to use a big data set, because that's not the point. I don't want you to wait for 3 hours. So I'm going to use a very small data set, 5 million points, just to show the point. So I'm going to, in Vex, there is an up-and-coming module, VexML. It's open source now, but it's going to be more open soon, when I have time to do it. Train and test split, again, this doesn't make copies. Whenever you do something like this, it doesn't make copies. It just looks into the big data. So if this was a billion rows data set, it will not take any memory. It will just take as much memory as you have here. So this test data set, we'll save it to disk. Oops, it's not defined. Maybe I need to run it. And now it's being saved to disk. I've run describe. I've filtered the data. I'm going to filter it again. I'm going to filter it again. More filters, more filters. We already did this analysis on the big data, so I already know what to do. I'm going to add some features. I'm going to add a feature whether something is a weekend or not. I'm going to create advanced features, so the distance, where I'm going, and this direction. So it's a complicated expression using trigonometry. I'm going to add them to the data frame, and they're here. And now I want to do some transformation. So in VexML, this sub-package, we have PCA, scalars, and categorical encoders that all work out of core. And basically, they obey the same expression as before. We can print this. Here is how the maps look transformed, blah, blah, blah. We make some choices about some other features that we didn't discuss. Let's say we label encode this. And what I maybe didn't say, actually, I'm trying to predict the duration of the taxi time. So we have some model, and I'm going to use, these are the features I'm going to use. I'm going to use LightGBM to train it. This is the LightGBM, I call it from Vex, but it's not actually fork. It's the actual LightGBM that you know and love, or you can use also XGBoost or scikit-learn or catboost. It just needs to be installed in your environment. It has nothing to do with Vex. We just call it from here. And then we can evaluate a model like this. So what happens here is I've trained the model. We've all done this, very nice. But I want to put this in production. And I have not created a pipeline at all. And if you've ever put something in production, pipelines are the thing that you make. But because we've had this expression system, every computation that I've done is stored in the sort of memory of expressions in Vex. So let's say I have this, we call it a state. The state of the data set I can save to disk. Oops. It's not defined. I need to run this. Now it's running the predictions. And of course, I have .predict method, which does it in memory. But I have .transform, which makes a virtual column, an expression of the data set. Now I can save the thing to disk. I go to the server, different notebook, load it up, print it, the standard thing, no extra columns. All I do is I apply this set of transformations, and I have all my predictions at the end. No pipelines needed. Here are the PCAs, here are the encoded values. Everything you need to do, the pipeline takes care of itself as if you do normal exploration in Vex. Thank you for the extra time. I hope you liked it.
Thank you. Yes, we were all at your lips. There's maybe time for one question.
Do you have somewhere also notebooks that do all this stuff in pandas to compare to?
Well, I cannot do this in pandas because I cannot open 1 billion thing in pandas.
Would be nice to see it crash, I guess.
So for certain things, we have benchmark comparisons, which are somewhat unfair because we do it on big data and they do it on small data. Depending on what you do, so we try to copy pandas. So some of their algorithms like group by and value counts are super fast. We're basically doing what they're doing. The only small improvement that we're doing is we do it in parallel. For other things like strings and many of the other computations, we have underlying libraries in C++ that take care of business. So it's fast because it's Python is the API, but the math is done in C++. But a fair comparison, it's difficult to do with pandas. On small data sets, it's the same. We're not faster. But what we can do is do this on billion rows. So pandas is great. We use pandas to read CSV files and so on. We get a lot of the inspirations from them, from the API, usability, use cases, and so on. We just provide a method to use instead of having chunks or clusters or maybe expensive things for the cloud providers, just to try your models quickly on your laptops or whatever machine you have. It works on Windows, Linux, Mac. Actually, all the stuff that you saw here are a bit slower because for some reason, we're heavily dependent on how fast you can read data from disk, because we're reading directly from disk. And on Macs, they have a buffer on how they have a impedance, how fast you can read from the SSD. I don't know why, it's their choice, there's nothing we can do about it. So if you use the same thing on Linux, you get double the performance or something, because they don't limit the speed you can read from the SSDs.
Well, thank you, Jovan.
Thank you.